In this video, we will look at a Boltzmann machine. This video was produced in Korean and then translated into English. The audio was generated by AI text-to-speech. In the last 6 videos, we looked at Hebbian learning and Hopfield networks. In this video, we will learn about the structure of a Boltzmann machine and look at the learning algorithm. And let's implement a simple Boltzmann machine in code. Let's take a brief look at the history of Boltzmann machines. Donald Hebb introduced the Hebbian learning rule, or Hebb's rule, in 1949. This is one of the earliest and the simplest learning rules for the neural networks. This rule is often summarized as neurons that fire together, wire together. John Hopfield proposed the Hopfield network in 1982. This is a neural network model that aims to emulate and understand the mechanisms of our memory that the brain performs when storing and recalling information. Hopfield used the Hebbian learning rule to train the network and applied the energy function and Boltzmann distribution of the Ising model to this neural network. In 1985, David Ackley, Geoffrey Hinton, and Terrence Sejnowski proposed the Boltzmann machine. Like the Hopfield network, this is also an energy-based neural network and is a generative model. A Boltzmann machine is structurally very similar to the Hopfield network, but there are some key differences. First, in Hopfield networks, neurons are binary threshold units, whereas in Boltzmann machines, neurons are stochastic units. Second, a Boltzmann machine consists of visible and hidden neurons. That is, a Boltzmann machine is stochastic Hopfield network with hidden neurons. Third, while the Hopfield network uses the Hebbian learning rule, the Boltzmann machine uses its own learning rule like this. In Boltzmann machines, every neuron is connected to every other neuron, making the network highly expressive but computationally expensive. Due to their unrestricted connectivity, full Boltzmann machines can model complex probability distributions. However, as the number of connections increases, learning becomes difficult. In particular, Gibbs sampling becomes impractical for large networks. In 1986, Paul Smolensky proposed a restricted Boltzmann machine, RBM, under the name Harmonium. An RBM consists of 2 layers, a visible layer and a hidden layer. The key characteristic is that there are no connections between neurons within the same layer. But there are fully connected, bidirectional, and symmetric connections between the visible and hidden layers. And in 2002, Geoffrey Hinton introduced contrastive divergence to speed up the learning of RBMs. This greatly improved the problems of the Boltzmann machine and finally made it possible to train RBMs on high-dimensional data. In this video, we'll look at the Boltzmann machine, and in the next video, we'll look at the restricted Boltzmann machine. The Boltzmann machine was proposed in a 1985 paper by David H. Ackley et al. The network modifies the strengths of its connections so as to construct an internal generative model that produces examples with the same probability distribution as the examples it is shown. Now let's look at the structure of a Boltzmann machine. A Boltzmann machine has a similar network architecture to the Hopfield network, but differs in stochastic update and learning properties. Additionally, we can add hidden units to the Boltzmann machine. Then, the Boltzmann machine consists of visible units and hidden units, and the input data is fed into the visible units. Hidden units are used to model higher-order correlations between visible units and to capture complex patterns and dependencies that are not possible with direct connections between visible units alone. They essentially act as mediators in the relationships between the visible units, allowing the model to represent a richer probability distribution over the input data. Even with hidden units, the learning rule for Boltzmann machines remains the same. Next, let's look at the energy function and the probability that a neuron will turn on. Let's take a simple Boltzmann machine as an example. Similar to the Hopfield network, the energy function of the kth data sample is defined as follows. This is equation 1 of the paper. The first term is computed as follows for I less than j. Here the superscript k is omitted. The second term, the bias, is computed as follows. An example of the overall energy landscape for S1 and S2 is as follows. Input patterns are stored at low energy spots. Then later, the network can seek out the spots and retrieve the stored patterns at those spots. Next, let's compute the energy difference when the state of the first neuron changes from 0 to 1. Let's calculate the energy when S1 is 0. If all S1 in the left expression are 0, the energy becomes as follows. Next, let's calculate the energy when S1 is 1. If all S1 in the left expression are 1, the energy becomes as follows. If we calculate the difference between the two energies, we get the followings. This is delta E, and it represents how much the energy increases or decreases when the state of neuron 1 changes from 0 to 1. Therefore, the energy gap, or delta E, can be generally expressed as follows. This is equation 2 of the paper. And the authors of the paper used delta E to define the probability that a neuron will turn on, that is, the probability that the state changes from 0 to 1, as a sigmoid function, as follows. Here, T is the temperature of the Boltzmann distribution and is a kind of hyperparameter. This is equation 5 of the paper. Next, let's create a learning rule for the Boltzmann machine. Let's take a simpler network as an example. This network has only 3 neurons and 3 weights. As with the Hopfield network, the Boltzmann distribution is defined as follows. The temperature T was assumed to be 1. Here, Z is a normalization constant that ensures that the probabilities sum to 1. There are 8 possible combinations of states for 3 neurons, as shown here. Calculating the energy for each combination gives us the following results. When I is 1 and j is 2, WSI as j becomes this value. And when I is 1 and j is 3, it becomes this value. The bias of each neuron was assumed to be 1. Next, We compute this expression to find the probability of the Boltzmann distribution. Z is the sum of these values. Then the probabilities are as follows. The probability distribution for each combination is as follows. The probabilities are higher in lower energy spots. That is, patterns are stored at spots of high probability or low energy. For example, MNIST image patterns are stored at these points. We define the log likelihood function as follows. Here, n is the number of training data points. Then we can update the weights by the following gradient ascent method. This is to ensure that the weights find where the probability is high. Now let's find the gradient of L with respect to Wij. Since PS is like this, the log likelihood L can be written as follows. Since Z is common, this just becomes log Z. So this expression can be written as follows. If we differentiate this expression with respect to Wij, we get the followings. And finally, we get this expression. The first term is the mean of SISJ and can be obtained directly from the data. And the second term is the expectation of SISJ given the probability PS. This can be obtained from the model. We'll look at how to obtain this value on the next page. Then the gradient of L with respect to Wij can be simply written as follows. Finally, the formula for updating W using gradient ascent can be expressed as follows. This is the learning rule for the Boltzmann machine. Next, let's look at how to calculate eData Sj and eModel SISJ. Let's say we have 10 training data points as follows. First, eData SISJ can be simply obtained as follows. For example, let's compute eData S1, S2. Out of a total of 10 data points, there are 3 cases where both S1 and S2 are 1. Therefore, eData S1, S2 is 0.3. Next, let's compute eModel S1, S2. First, we use this formula to calculate the energy gap for each neuron. Let's assume that each bias is 0 and t is 1. This value means that for the first training data point, when the state of the first neuron changes from 0 to 1, the energy increases by 0.2. Next, we use this formula to calculate the probability that each neuron will turn on. This value means that the probability that the state of the first neuron will be 1 for the first training data point is 0.55. Next, we sample data from these probability distributions. This value means that the probability that the state of the first neuron is 1 is 0.55. And the probability that it is 0 is 0.45. So the probability of getting 1 is slightly higher. Let's say we sample 10 data points in this way. In this sample set, there are 4 cases where both S1 and S2 are 1. So the eModel S1, S2 is 0.4. Now that we know these values, we can update W12 like this. Alpha is the learning rate. The W12 is updated from 0.2 to 0.19. Finally, let's implement and code a simple Boltzmann machine without hidden neurons. As we did in the Hopfield network, let's store these image patterns in a Boltzmann machine and reconstruct the corrupted image patterns. The input data is as follows. Initialize the weights randomly. Update the weights by the learning rule. Randomly choose I and j. Compute the mean of SISJ from the data. As we saw on the previous page, we compute the expectation of SISJ from the model. Update the weights using gradient ascent. Repeat this process many times. The corrupted image patterns are as follows. We get the output of the network using the weights W and the probabilities pk. The results are as follows. While updating the weights, the energy decreased as follows. And the corrupted images were successfully reconstructed as follows. Let's run this code. We got the following results. In this video, we looked at the Boltzmann machines. In the next video, we'll look at the restricted Boltzmann machines.